Alright, so hello and welcome. This is the classic n-queens problem, and this is n-queens 2. Basically, they just had the same problem twice on LeetCode, where one of them was looking for a count of the solutions, and the other one was looking for actually, like once you found the solution, to go ahead and like print the board state as a set of strings. So they're slightly different from each other, but not too much different. So n-queens 2. We're basically just going to take our n-queens solution that we had before, copy paste it, and use that slightly modified version for n-queens 2. So yeah, this is going to be super short. I mean, I don't know. I mean, it's there, right? Like, we'll just do it. So again, n-queens puzzle is the problem of placing n-queens on an n by n chessboard such that no two queens attack each other. Given an integer n, return the number of distinct solutions of the n-queens puzzle. So that's pretty much the same problem over again. N is 4, output 2 distinct solutions. The 4 queens puzzle shown as shown, and then n is 1 is only 1, and we're going to slightly modify a previous func program. So we'll quickly go through what the program does. You say, so instead of ret being this board state, it's going to be an integer. We'll start off at 0. And we're going to say this part we can and then we could just get rid of this part. So we have a state. We're going to say each row is going to get its own vector of integers to count how many queens, either if there's a queen there or not, and also how many queens are watching that particular area. And we're going to use a depth first search through that state, changing that state as we add queens. In the base case before, what would happen is if we get through, we place all of our queens and all n queens, then we would convert those states to the board state. I guess the quote-unquote correct board state, or the where we would convert that to the representation, the string representation of that board that they wanted. And that was a little bit of code here, but actually what we can do now is just ret plus equals plus plus and return. And then this code I think stays the same. So we loop through each column in that particular row. If there is, we set x is going to be the value in that state at that column for that row. And if it's a 0, we could place a queen there. If not, we can't place a queen there. Either another queen is guarding that spot, or well, actually, really, it should be the only scenario. When we insert a queen, we set that state to -1. Right, that's for later when we want to. We've recorded the state where we don't actually need that anymore. But we're going to add that anyway. Actually, we don't really need it. We could just remove it. Don't need to do that anymore. And then we would also update the diagonals that the queen is guarding, and we have a routine to do that. That's basically each row below that row, that spot, all the columns that have the same value are going to get set. Are going to get a +1, and all of the diagonals. So the way the diagonals work is you just increment the right diagonal, you just increment each row, and the left diagonal you decrement each row. So you get all the diagonals get incremented, and the straight down portion gets incremented for all the rows beneath. And then you recurse, right? That queen is placed, recurse, and then once you remove the queen, you remove that queen. Now after you've recursed, when you remove your queen, you remove all of those diagonals that it was watching, right? So those all get decremented again. And so it's a pretty simple for loop you can do. Just each point you decrement the left diagonal and increment the right diagonal as the, also I think that's not how you spell diagonal, it's D-I-A, not D-I-A-A-I. So that's interesting that I spelled that incorrectly every time. We're just gonna fix that. I'm not gonna fix that in the other piece of code, but that's interesting that I got that wrong every time. I thought that looked weird. Something about that didn't look right. Yeah, so this should be correct. And as I said, should be like pretty much a quick, like, few minutes video, just explaining the solution again. Yeah, it should be You can name your variables whatever you want, it'll still work, but it should be. Yeah, so now we don't actually have to modify the port state at all like that. So dag. Oh, yeah, of course I missed something somewhere. Let's see if it compiles. Oh, whoops. Let's see. Okay, and then we'll test. 1, 2, whoops, 3, 4, 5, 6, 7, 8, 9. Again, this is one of the few problems where you can actually test every single test case to make sure you got it right. And it looks like we're correct. And it looks like it runs in 0 milliseconds. That's nice. All right. Interesting that it runs in 0 milliseconds the first time, but on their test case it's 4 milliseconds. Give me the full one. Give me the 100%. All right, so that's 6 minutes we did here. Okay. Yeah. So we'll go ahead and wait 1 second to try one more time to submit to try to get 100%. For some reason we got 0 milliseconds our own test cases, but we didn't get 0 milliseconds on theirs, which is really annoying. That's funny. Oh no. It's hysterical. All right, we'll wait few more seconds, and then we'll be done with this one. But yeah, that's a fun problem. Basically, just explained the solution again, and just slightly modified this so that we would get. All right, well, whatever. That's fine. No big deal. We got 0 milliseconds here, right? So yeah, thank you for watching that one. That was just really just like it's the same problem as the other one. So there's not much to go over there. So yeah, thanks again. Take care. We're gonna pick up another problem soon.